Presented by Caltech.
Hi everyone, thank you so much for coming to our most well-attended IQIM seminar to date. Apologies in advance for the food situation. There will be food after the question and answer session after the talk. We're really happy to have John Martinis here from Google talking about the recent quantum supremacy announcement. This is the first talk to a scientific audience since the announcement, so we're really happy that we can have it here at Caltech. Without further ado, John?
Yeah, thank you for the wonderful invitation. It's really great here. You know, we started seeing these results about May and June, and it's really hard for a scientist not to talk about some great results for months and months. So it's fantastic to be here today, especially at Caltech, where you know, my physics hero is Richard Feynman, and who kind of invented the ideas, and to come here and talk at Caltech, and also with John Preskill here, of course, for the quantum supremacy is great. After my talk, we're going to have a Q&A session, and I try to arrange it that we're just going to stand here and answer your questions till there's no more questions. And we'll see how that goes, if I can you know, do that. You know, we understand there's a lot of new stuff here that is going on. People have a lot of questions. Paper's kind of complicated, so both Sergio and I will be here to answer both the theory and experimental questions. And in some sense, that will be the most fun part of this, because we want to see what people are thinking about and answer those questions. That's a very important part of the scientific process. Okay, so quantum computing was thought about, invented in the 1980s. That's over 30 years ago. And of course, we're all very interested in it as a possibility to build a very powerful new kind of processor for certain kind of problems. And since then, there's billions of dollars that have been going into it worldwide. There's billions of dollars that's going to go into it into the future. And my question and our question was like, well, how do we know this is really going to work? And especially if we're going to put billions of dollars into it, we probably want to do an experiment to check if this thing is going to be powerful as soon as possible, even if it's not that useful or marginal, whatever, and do that. And of course, the quantum supremacy proposal by John Preskill fits into that. So that's what we've done with the particular algorithm we're going to talk about today. So, you know, physics has been promising this for many years, and, you know, can we deliver? So I had the distinct pleasure of giving a White House brief last week, and I was trying to explain this idea that, you know, we've been working on a long time, and we need more support, and this is a great result to the senior White House people. And I decided I would sell it to them by using the phrase, you know, describing about physics, promises made, promises kept. And I think they really liked it, because we got 2 tweets the next day, one from the White House and the second one from Ivana Trump. So, you know, that's almost the pinnacle of you know, being tweeted about, almost. You know what I mean. Okay, now, one of the things I want to point out is this is a hard experiment to do and get all this stuff to work in a system. And we purposely did a hard experiment which could possibly fail. That's what was so hard about it. And normally you don't do things that you can possibly fail because you're worried about getting your funding cut, okay? But we wanted to do a hard experiment right away, so if we failed, we would fail as soon as possible so that we would know what to fix, and we would have the time to fix it in order to make progress and go on to bigger things. So that forced us to be very careful to solve the hardest part of building a quantum computer right now, which I'll call quantum systems engineering, to get everything to work at the same time. And it really forced the whole group to address the big problems and fix them and invent a bunch of new things that we'll be talking about here today. And of course, what's nice is if you do this experiment successfully like we did, the next step of doing error correction or whatever is just a further step along the path, and we learned a lot to be able to get there. So in terms of what I'm going to talk about today, we're going to talk about what made this happen, which is the new design of qubits, which are both scalable and have very low errors. And by doing that, we were able to do this quantum supremacy experiment where 200 seconds of data taking on a quantum computer is checked in a very long time, and the algorithm we ran was maybe 10,000 years. This is computation on a huge, about 10 to the 16 computation or Hilbert space, and that's way beyond what people have been done. And then the fidelity of this was validated with 1 and 2 qubit errors, which means there's no additional decoherence physics when we have scaled up. And that's really a very important observation, and I'll explain what that means. First useful application, we're certified random numbers, and I'm hoping this is the beginning of a NISQ era with powerful processors, and hopefully we can do more useful things with that. Okay. So we're building quantum systems out of not atoms or molecules or normal quantum objects you're thinking about, but making them out of superconductors, or we're making them out of electrical circuits. And these particular qubits, these particular quantum systems, have a macroscopic number of atoms in it. And because of that, it's kind of a new kind of quantum system. There we go. It's a new quantum system that really didn't exist until the mid-1980s when myself and John Clark and Michel Devereux started building these at UC Berkeley. And of course, there's been a huge network of people around the world working on this technology. And it's really a new kind of quantum system where the currents and voltages are quantum mechanical objects and thus can obey quantum mechanics. So how do these work? These are electrical circuits, electrical resonators that are essentially inductor-capacitor resonators. So the great thing about these engineered superconducting qubits, they're macroscopic, they're easy to control, and when you look at a picture here of the particular qubit, we bring on our wires here to control them, and there's room for wires to get in there and do that. And you're doing microwave controls, which are easy. It has engineered properties, electrical circuits, so we can do a lot of different kind of engineering to get it to work. And of course, it's microfabricated like a computer chip, so we know how to scale it up. And then the qubit is basically formed like an LC oscillator, where Josephson junctions, which are just two metal strips separated by the thin oxide barrier, forms essentially a nonlinear inductor. So you have a nonlinear inductor capacitor. And essentially, the ground state is what you encode as the 0 state. And the first excited state, which you can think of as an oscillating pendulum, oscillating LC, is the first excited state. And then we have control knobs coming in here to both excite the qubit with microwaves, and a control knob here to change the frequency of the qubit, which gives you phase control. So let's go on to the Sycamore processor, which is 54 qubits, which is given here. And the X's are these superconducting qubits, this nonlinear LC oscillator. And what's new about this whole architecture, brand new, is we have an adjustable coupler in between all the qubits that can turn on and off the interaction. So we have full control of whether these are isolated or they're coupled to their neighbor. So that's what's new. And here's the chip. It's a few centimeters across. You have about 200 wires going to the outside, which is going to all our control circuitry. And these bring into here, and we have a qubit chip on top of that. And this kind of bump-bonded, indium bump-bonded chip is how we make the device and use the device. So we have our fabrication here, and then we put it in packaging where we wire bond this to a circuit board, and those wires go out to the bunch of microwave connectors. And then this whole package goes into the dilution refrigerator where we have wiring to a bunch of filters and amplifiers or whatever at 10 millikelvin in the dilution refrigerator. And then those wires go up to room temperature to our control electronics. And that control electronics, you can see here, goes from the top, and you have a bunch of wires that go to racks of electronics, of custom electronics. And these are basically microwave and pulse synthesizers. You can buy that easily. We make them custom built to be high speed and low noise and high precision to be able to control this. And then, of course, there's a huge software stack not seen here, to control everything and make sure everything's working properly. So this kind of looks a little bit maybe like a small high-energy physics experiment. And we're certainly not afraid to do a bunch of wiring at this point to get this to work properly. So I want to explain a little bit about how this adjustable coupler works. So again, here's the Sycamore architecture now tilted a little bit. And what we have is the qubits now are in red, which again are these nonlinear inductor capacitor resonators, okay? And then in blue, we have coupling of these, the qubit to a readout resonator. This is resonating at about 5 gigahertz. And what happens is when these are placed off resonance from each other by about 1 gigahertz, say that's 5 and that's 6 gigahertz, and when this goes from a 0 to 1 state, its effective oscillation frequency changes a little bit. Then because of off-resonance coupling here, this frequency changes by about 1 megahertz. And by putting a microwave signal into here and kind of probing what resonance frequency we have here, bringing it out again, you can then figure out the qubit state. So this is called dispersive measurement. What's new here is we have coupling between the qubits that can be adjustable. So let's just look at this part of this here, and let's just ignore the junctions here for a second. So you have a capacitor to ground, another capacitor to the other qubit, and this is nothing but a capacitor divider circuit, so that if you have some voltage fluctuation here, you'll get some current into this, and then some current into the other qubit, which will excite the other qubit. And this looks just like a capacitor coupling, and you can write down the Hamiltonian for that. What we do is we put a junction here, so this is resonant qubit, then this resonance is above the qubit frequency, and the resonant means you get a little bit stronger interaction because of the resonant buildup of the fluctuation from here going into here. And then what happens is because this frequency here is lower than this frequency here, you're mostly seeing the inductive response, and thus the net coupling through here is not just the capacitive division, but there's a phase shift from this. So this coupling here looks like a negative capacitance. And this negative capacitance can be changed by changing the frequency of this LC resonator by putting current and flux into this loop. So you change the frequency here, and it resonates a little bit differently because it's off resonance, and it'll build up in a different way. And that way you can adjust the effective negative coupling from here to here. And then by putting a physical capacitor from here to here with positive capacitance, that means if you tune this up right, you get 0 net coupling from here to here. And that's what we want. We want to be able to turn it off. Because it's not just be able to connect the qubits that you need to do, but you need to operate them in isolation. And to be able to turn them on and off effectively this way is very important. So this is a calibration experiment we do. Okay, we have 2 qubits, and they're originally off resonance, so they're optimized in some way. And then to do the 2 gates, we put some current into here, which changes the frequency of this oscillator so that they're at the same frequency, and then they could start to interact. And then what we do is we turn on the coupling for a very amount of amplitude and a very amount of time, and then we wait to see what happens and then measure one of the qubits at the end. So here's the results. This is actual data. This looks like theory. This is data, okay? This is the coupler bias, which is changing the frequency here. And this is the time. And then what you see, let's say here at 0 coupler bias, that this occupation is initially going from 0 to maximum, 0, maximum, 0, maximum, as the coupling here is causing the excitation of this one photon to bounce back and forth between Q0 and Q1, and then you measure it. And from the period of this, you can get a net coupling of that of a few megahertz or something. You change the coupling, you change this effective negative coupling, and at this point, the oscillation goes away, and you say that the coupling between them is 0, and then it's off. And then you change this a little bit more, and then this gets to be a lot negative capacitance, negative coupling, and then you turn on the coupling between this, and you see very rapid oscillations. So this is really nice. We can turn this off to about 10 kilohertz or so, and turn this on to 40, 50 megahertz or so, with a pulse going in here with about a few nanoseconds, about a nanosecond or so time resolution. So we can fully control what's going on. And this particular coupler here, and be able to turn it on and off, especially turning it off, enables us to make very good system performance gates and to get this tuned up, and also to make very fast gates. So the speed of these gates here that we're going to be used are about 10, 15 nanoseconds. They're even faster than the gates that we're making with the qubit. And that's really unusual in the field, that 2 qubits are faster than 1 qubit. But you can do that. So when you make this device, you go ahead and you want to measure how good is it. You want to measure the errors. So what we do is we do a bunch of gates on it, and then we check what the final answer is, and we check how close is the final answer to what we expect it to be. And then knowing that there are a certain number of gates, you can say on average that there was a certain error per gate. And quantum mechanics intrinsically gives you errors. You're always going to see that. And we measure that for the whole gray. So for single qubits, what we do is we measure all those errors, and it ranges from about 0.1% error to almost 0.2, 0.3% error. And there's a histogram. This is an integrated histogram. So you can see that the mean is over here, and then there's a width of that. So the average single qubit error is about 0.15%, which means you can do 600 or so, maybe 1,000 operations before your qubit loses its memory on average. Okay, we can also do that with the 2 qubits, where we do this interaction and make an appropriate gate, as we talked about the other time, and that number is actually around 0.036. Okay, and it's about twice this. You expect it twice as much because there's 2 qubits. So this is actually pretty good, and this is kind of a record for what we've been able to get this system working this well. And then you can look at the individual errors here over the whole array, both for the single qubit and the 2 qubits. And there's no obvious pattern here. It's just we're getting a random distribution. Okay, so up until now, these kind of numbers are very good. It says you can make a good quantum computer and the like. But these numbers are still a little bit fake, okay? And they're fake in the sense that they were measured in isolation. We turned off all the other qubits, all the other couplers, and measured this, and then did it for all the other ones. We turned up all the other qubits and measured their coupling here and isolated, and then we got this number. But that's not how we want to operate a computer, a quantum computer. If you want to make it fast, you want to make it powerful, you want to turn on all the operations for the qubits and turn them all on for the different couplers all at once. You want to do it simultaneously. I mean, that's what's going on in here. There's not one transistor switching every clock cycle. There are billions or millions or billions of them, and that's how you get the power. So we do the same experiment where now we turn off all the couplers and then just do all the individual experiments all simultaneously. Okay, and there's a lot of things that can go wrong with crosstalk and the like. And when we do that, we just get a little bit worse error. So there's very little change here. When we do the same thing for qubit pairs, so let's say this pair here, and this pair here, and this pair here, again, also simultaneous, that's a little bit more than here. So we have some crosstalk here, but it's not that bad. And what I would say is, as people are starting to use quantum computers and build quantum computers, just don't quote your best or isolated values. You really have to know what happens when the whole thing is working at once. You're building a system. And simultaneous good errors is really what you need to do. Now, I'm going to try, one last thing. When we do this interaction between 2 qubits, you're kind of getting a swapping interaction. And you can talk about that in terms of unitary matrix, between 0, 0, 0, 1, 1, 0, 1, 1 of a swapping interaction where you can adjust this parameter and turn a 0, 1 into a 1, 0. And you can do this with an arbitrary angle. There's also some interaction of the 1, 1 state with the 2 state of the qubit, and you can also put in a phase factor in this 1, 1 state if you do this. So this is kind of the general purpose unitary interaction you can get between qubits that we're able to synthesize experimentally. What's really cool is this particular subspace of all possible two qubit interactions is actually this excitation preserving kind of unitary maps very well if you want to do a near-term application of fermionic simulation for quantum chemistry, which is, of course, what Feynman talked about, where that has some excitation preserving. So this particular way of making the gate is very powerful, we think, in the future for doing simulations of quantum systems. And we're working hard on producing this. So here's an experiment by graduate students. He's writing up his thesis now, where we've looked at, I think, about 40 swap angles between 0 and 90 degrees, and about 40 phase angles here between 0 and 40 degrees. And wherever you want to get in here, we did an experiment to synthesize that particular theta and phi, and you see that the error that in doing so and making these unitary gates is in the low to mid 10 to the minus 3. In fact, if you integrate histogram that, you see it's around average of about 3.8 times 10 to the minus 3. So we can make very good, well-controlled gates out of this device and know exactly what's going on and build an arbitrary programmable quantum computer. Now, for the particular algorithm we're working on today, we're going to build gates that are around here because that was kind of easiest for us to do. That has both swapping and some phase to it. But again, for an arbitrary algorithm, we believe in the future we'll be able to make it more general and make it fully programmable as you want to do. Okay. One of the other things I want to talk about here before getting into the results is that this whole calibration process of putting in microwaves, putting in the pulses, you have to calibrate your quantum computer. And this is, in fact, the hardest part of making a quantum computer. We spend all of our time on that. And, of course, what happens is we've been learning to do this over 15 or 20 years now, and there's a lot of knowledge and expertise built into it. But when you want to build a 50-qubit device, you have to automate all that. You can't have a graduate student tuning it up. That's what you start with, but you can't do that for very long. So the calibration is actually some computer program that goes ahead and systematically goes through that. And this is a graph that describes the calibration of the electronics and device parameters and single qubit gates and readout and 2-qubit gates that talks about how to do this for 2 qubits. So one node is, you can think of one physics experiment. There's thousands of nodes for the 50 qubits. And just to give an example, Jimmy Chen's PhD thesis were these 2 nodes here. Okay, so there's a lot of expertise in here, both by our group and everyone in the field. You really have to do that. What's nice is once you understand the physics, you write your PhD, and once you do that, you can write code to automatically do this. And it takes us, let's say, about 2 minutes to calibrate a single qubit. So it's reasonable. And then from scratch, and then to do it better is even faster. So this is a big part of it. Given the results we had for the 2 qubits, I just want to take a side view for a second, and then we'll get on to the quantum supremacy about error correction. So right now, we're building quantum computers that have errors, and we're trying to see what we can do with it. But in the long term, we want to do quantum error correction so we can do quantum operations with essentially no errors at all, and then do much more complicated algorithms where we know there's a use in classical speed up and the like. Now, to do error correction properly, you have to be lower than an error correction threshold, or else the errors are happening faster than you can fix them. And that error correction threshold is about 10 to the minus 2 error, about 1% error for the 2-qubit gate. That's the hardest one. So above that, you're kind of in the death zone, where no matter how many qubits you can make, you're not going to error correct it. And I'm going to say most quantum computers these days are up in the death zone, okay? And then, of course, you want to be below that, maybe a factor of 10, so that you have enough error correction gain to be able to reasonably make it. When we started this in Santa Barbara, we were just dipping our toe under this threshold. We had a one-dimensional array, about 9 qubits, connected to their 2 nearest neighbors. And what we were able to do with the Sycamore chip is to go from 9 qubits to 53 qubits, which is good, more qubits. But we've also gone from a one-dimensional array to a 2-dimensional array, which is what you need to do the error correction. And we've gone from 2 connection to 4 connection, which, of course, there's more possibility for things to go wrong. And doing all that to get more qubits, more connection, less errors, all at the same time in a system, that's what's really hard. And and we have to continue to do that. If you look at that, we need to get the errors down to 1%. So we're moving in this direction, and hopefully we'll be okay. Note that if you look at the isolated, you look at some of our other experiments, it is possible to get the errors down a few things. So we think we can bring this down. It's just going to be harder. And then, of course, once we get down here, we're going to want to scale up to, say, about 1 million qubits or so, where you can start doing error correction, and then you have enough logical qubits left over to actually do a calculation. Okay. So that's kind of where we are, where we're going in the right direction. We have a ways to go. Now, I want to make a point here, is I'm plotting here the 2-qubit error, the hardest error, done simultaneously, which is great. So we're doing that. But how do we know when we build a complex system that these gates are still appropriate for the whole system? Okay, you don't know that. You think it's going to work, but all these things can go wrong. And what you need to do when you build a big quantum computer is to do a system validation to make sure that, whatever errors you're getting here, measuring in the way I talked about, it's still going to limit what you're doing in a complex quantum computer. And that's what, as an experimentalist, is kind of what the quantum supremacy experiment is about in terms of moving forward and doing all this, is system validation. And it's a really great way to do that. I think it's very beautiful, the idea. So let's talk about how this is working. Okay. So this is a summary of the algorithm for doing this quantum supremacy experiment. And of course, we have simultaneous gates on all qubits. And what we're doing is we're interleaving single qubit gates, which are a single circle, to 2 qubit gates, which are connected circles. And since there's 4 connections, you're just rotating around over time the different connections to do that. And you see that we're doing a lot of gates at the same time, as we're doing this. And this kind of simultaneous operation connecting to all the nearest neighbor gates is actually a general purpose algorithm for using a quantum computer, this kind of quantum computer. If you want to do a real algorithm, this is essentially the sequence you're going to use. You may change a few things. You may change the single qubit gates. But this is a general purpose. So the quantum supremacy algorithm is really testing a very general purpose algorithm of the device where you're cycling through the 1 and 2 qubit gates. Now, if you were to isolate one of these qubits, say in the center here, you see that the particular sequence is we start in the ground state, and then we put it into a superposition state of 0 plus 1. And we can do this, in fact, in different directions to have a different phase of the state. Around the x-axis, around the y-axis, the w axis in between them. And these particular rotations are chosen at random. Then we do this fixed 2-qubit operations to the nearest qubit to kind of start entangling the qubits, getting them to talk to each other, and then another random gate, and then the next neighbor in another direction, another random gate chosen randomly, another gate, etc. We do that for cycles which range from 12 to about 15, and then at the end, we measure what we have. Okay, so it's kind of a general purpose algorithm, but we're choosing these random gates. And of course, since these are chosen random gates, randomly chosen gates, you expect all possible combinations of the outputs to come out of here. Okay, which sounds like that's not very interesting, but it turns out it is. I'll talk about that in a second. In terms of these single qubit gates, we have microwave pulses of about 25 nanoseconds in length. And between these couplings, we have changed the qubit frequency, and we change the coupler to get them to turn on and off in the way that we want to do that. Okay, so that's the basic idea here. Okay, so now let's talk about the algorithm, the validation algorithm for doing the quantum supremacy experiment. So again, this is checking a general purpose circuit, but we're particularly choosing random gates because they have this amazing special character to it that we totally take advantage of to do some really interesting physics. And what is the thing is the randomly chosen gates gives us qubit speckle, very unique qubit speckle. So the way I like to explain that is you take a laser and you go through a piece of ground glass. Okay, that's going to diffuse out the beam. You're going to get a spread of the beam, as you kind of can see here. But what's going to happen is because it's a coherent laser beam, some directions you coherently add and some directions you comparatively you subtract, so that you see a speckle pattern where some directions are bright and some directions are dim. And the particular speckle pattern you get depends on the details of the speckle pattern of the glass. So the same thing happens with these gate sequences. You get qubit states in all directions and all 2 to the n states, but some of those probabilities have been constructively interfered, and you're going to get a higher probability, and some qubit states are going to be lower probability, okay? And where's high and where's low is uniquely determined by the set of random gates that you ran. And in particular, and this is the important point about doing this, we use this to our great advantage in this experiment, is that if you have a single qubit error anywhere here, you did a bit flip from 0 to 1, or you had a phase flip where you added pi to a phase, then that speckle pattern completely reorients and it's different. It's totally not correlated with the old speckle pattern, okay? And we use that to our advantage to actually do a systems test of the quantum computer and to also show quantum supremacy, okay? And in order to understand what that speckle pattern is, you have to simulate on a classical computer what this circuit does. There's no structure in here. It's complex. It's random, so that you kind of just have to do a brute force integration, like Schrodinger integration or some other tricks to do it. There's no trick you can play to do it. It's known to be a complex generation of a quantum state. And because of that, when you make this big enough, it's very complex and difficult to simulate. At some point, you can't simulate it, and then you say you're in the quantum supremacy regime. So this algorithm, we use it for 2 things, both for validating our quantum computer and then also for showing that quantum mechanics is really complex, computationally and through here. So there's 2 things we're doing at the same time. Okay. So here's our circuit. We choose a circuit. We run it on our quantum computer. And then we get bit streams, 53 zeros and ones. And we do that maybe 100,000 times or 1,000,000 times. So you get a bunch of bit streams. You take the circuit and you run it through a supercomputer, and you get the probabilities of the 1 to the 2 to the n states. Okay, those are the two things you do. You then cross-check whether you got the speckle pattern you expected using something we call the cross-entropy fidelity, where we take the bit streams we measured and look up what the probabilities we had for that bit stream that we computed. Now, if you kind of randomly select from all of this, on average, no coherence, that'll average be a probability 1 over 2 to the n, and the fidelity will be 0. If it's a perfect match, then the states, the kind of distribution of states you get, this particular, you're going to see the high probability states because that's what you're measuring here, and then the formula turns out to be 1. Okay? So what you have to remember is that when we do cross entropy, if it's a perfect match between the quantum computer and the simulation, no errors at all, you're going to get a fidelity equal 1. And if there's one error or more than one error, only one error, bit flip or phase flip, you're going to get a 0. And then what's nice is you just do the experiment and you can see how well the system is doing for the whole quantum computer, and check that. And of course, at some point, you have so many qubits that you can't do this anymore, and then we run an algorithm that can't be checked with classical computer, and we get quantum supremacy. So again, cross-entropy, system validation, we can learn the control map, we can learn a lot about what's going on here by understanding this fidelity, and very, very useful besides just showing this. Okay, so let's get to the data, finally. Okay, we run a circuit, let's just take this point here, with 12 qubits, and we run it for 14 cycles, which each cycle is a 1 and 2 qubit gate. So that's 28 plus 1 at the end is 29 operations. So 12 times 29 is a few hundred total gates. We then measure what the output states are, and then we check them against what we predicted with the cross-entropy fidelity, and we get this red circle here. Okay? And we see this is about 40%. So 40% of the time, with hundreds of gate operations, we're not getting any error. Okay? And then we increase the number of qubits. And of course, when you add more qubits, you're going to have more chance of error. And this cross-entropy fidelity goes down as expected. And it keeps on going down and down and down until we get to this endpoint here at 53 qubits. And we have a fidelity that's a little bit below 1%, but this is way bigger than the uncertainty for taking 1 million qubits. So we know that it's a positive and real, and there's some fraction of our events that are operating totally without error. And of course, on this particular case at 53 qubits, that's hard to simulate. This particular one took about 5 hours on 1 million cores in a Google data center to check here. And you see it's a nice line that goes down as you expect. Now, one of the interesting things we can do is we can simplify the circuit and see what happens. Okay, the easiest simplification we can do is just turn off the 2 qubit gates right in the center of our system. Okay? And when we turn off the 2 qubit gates, they're acting independently. Okay? And that's much easier to simulate this acting independently of that. And it's much easier to get that. And then when we do that, we see that it more or less gives us the same value. You can also do something in between where we take this cut and only put a fraction of those 2 qubit gates, coupling it together. So it's still entangling between the two states, but because it's a fewer number of gates connecting them, it's called lighted gates, it's easier to simulate. And again, you get this, you basically see the same answer here. So these are nice because this is less computationally intense, and you see since it gives the same answer, we can say, well, okay, we kind of can understand that with an easier validation sequence, we can kind of understand what our qubit system is doing. Of course, you have to go to the full system to know for sure, but we can test it in these other ways. Now, this is data that we can simulate with 5 hours. It turns out the reason you can simulate this is there's some mathematical trick to the algorithm that allows you to combine together the gates to make it simpler. If you just change the circuit sequence in some, it looks like a trivial way, but it's a very important way, it turns out you can't play that mathematical trick, and then you're in the supremacy regime. And in that case, we've taken 53 qubits, but instead of the number of cycles being 14, we have 12, 14, 16, 18, 20 cycles. Now, we can't verify the circuit anymore, which is the red circles. It's too complicated. This would take weeks or years or millennia to do that. But what we can do is we can use the simplified circuits that are lighted and patched and do that. And then we say, you know, we're going to be fine. And since we know from here that all these cross-entropy fidelities are consistent with each other, we believe that if we could simulate this, this would be enough away from zero that we can claim the quantum supremacy. So that's kind of the way we claim quantum supremacy, even though we can't exactly simulate it because we've done these other check experiments. Okay? Now, I want to point out what is the most amazing thing about this data and why, if you want to think about it in a funny way, why we can all, our quantum scientists can all keep our jobs. Or maybe get more funding, even better. Okay, and this is the data. Look at this black line here. This black line more or less aligns right over this full secret data, but it's just a simple prediction from the 1 and 2 qubit simultaneous data that I showed you before. You take the errors for each operation in the circuit, and you say that the fidelity is 1 minus the error. You multiply all those fidelities together in a totally classical way. This is high school probability theory. And it predicts what's going on in this very, very complicated system with all this quantum computation going on. That, to me, is absolutely amazing that such a simple model for errors works so well. Okay? That was the big, when we got the data, when that happened, it was the big surprise here. Okay? And of course, if things were worse, you know, I wouldn't be standing here talking to you today. So this is good news. So let me just go into that a little bit and just say, this is amazing. We have a full circuit. We cut it in two. We partially cut it in two. We predict it with two curves. Errors do not depend on the degree of entanglement and computational complexity. When we're doing the 1 and 2 qubit experiment, that's a computational space of 2 and 4. And errors from a computational state of 2 and 4, just using classical probability, predicts what happens when you do a computational on 10 to the 16 states. That's amazing that it works, okay? So it means if errors do not depend on computational complexity entanglement, only on how good the individual gates are, then we should be able to do quantum computation. I mean, that's the assumption we've been making all along that for this to work. And we have real good proof from, you know, a large computational space that nature is really this way. There's no additional physics, no additional decoherence physics, either practical or fundamental. And to me, that's amazing. Again, error correction should work. Fidelity is predicted. Previously, people tested this idea on a computational Hilbert space of 10 to the 3 or so. Here we've tested it 10 to the 13 times bigger space, more complexity. And we all know in physics we want to push the limits of how we understand physical theory. If we've changed some parameter in the physical theory by 10 to the 13, and the essential quantum mechanics physics doesn't change, that's kind of amazing, and it really shows how beautiful and how well quantum mechanics works. And we should be able to use it. That's what's really cool. I wanted to talk about one last thing, is I said this particular algorithm we used was based on the fact that you lose to fidelity if you have a single error. And this is data here, taken, I think it's about 20 qubits or so, something with a reasonable fidelity of a 20-something%. And we took the hundreds of gates, and we randomly chose one gate, and on that gate, in the simulation, the computation, we put a phase in the algorithm, the simulation, that was not in what we ran in the quantum computer. So it's a z rotation on the Bloch sphere from 0 to 2 pi. And when it's 0 rotation, so there's no errors, you see the full fidelity of about 20% or so. And then when we put a pi rotation here, that's called a phase flip error, full phase flip error. Indeed, that error goes to 0. The fidelity goes to 0. As I've said, one error gives 0 fidelity. So we can check this. We've checked it simulation. We can check it with the quantum computer. The interesting thing here is what happens when you put a partial rotation here. So you do a pi over 2 rotation, and then it goes down by about a half. And in fact, if you look at the experimental data, it's fit very well with the fidelity times cosine squared of theta over 2 curve. And cosine squared of theta over 2 is just the probability of doing a pi phase flip if you have a continuous rotation. This is the measurement formula for quantum mechanics. And what this does, it's a very beautiful test of this model that you can treat errors in a quantum computer in a digital. You have a continuous error here, but you can treat it as a probabilistic model of errors, which of course is something we're assuming in quantum information science, but it's nice to show that it works and you can do detailed tests. And there's a lot more going on that you can look at there. But again, it shows that some of the theory people have been assuming for years and years on how a quantum computer works, you can kind of validate it in this way. I'm going to talk for a second about the simulation cost as I'm going to get into the next thing. And these are plots of simulating how much computer times, classical computer time, it takes for simulating a quantum system. Here's the number of qubits going from about 10 to 70, and here's kind of the depth of the circuit, the number of cycles, and we're kind of around this range here. This is what we call the Schrödinger algorithm, which is exactly what you would think. You take the Schrödinger equation, you make a Hilbert space of 2 to the n, and then you just integrate the Hilbert space time step by time step to figure out what the result should be. And you know, when there's a few number of qubits, it takes maybe a minute to an hour on your laptop. If you use a supercomputer, you can go up to more qubits for a minute and an hour. But you see here it grows exponentially in the number of qubits. In the number of cycles, since it's linearly complex in this way, there's not much going on here. You can see, though, that this has severe memory requirements where you have to store the quantum state in the quantum computer. So that memory goes as 2 to the n. And you know, in a laptop, you can get up to a few gigabytes. And in the supercomputer, you can get up to a petabyte or so, which is right here. And if you want to use the disk, the hard disk drive, slow hard disk drive, on a supercomputer, you can get a little bit more about here, which we'll be talking about in a second. And so we can do simulations here, and then we can do simulations up to on the Jülich supercomputer, then get some results here and do that. But as soon as you get beyond too much memory or so, this gets really not the way you want to do it. The way the simulation worked is that we basically broke up all the qubits into 2 halves, solved each halves with the Schrödinger equation, which because it's half, it's way, way exponentially easier. And then we connect them together with essentially a Feynman path integral kind of idea. And then what happens is now you see that the memory requirement is you know, a square root of what you see here. So in these number of qubits, you have a reasonable amount of memories. But now, because you have to connect them with all these Feynman paths, it gets more and more complex as you make it more and more complicated. So this is the results we had that we were able to simulate up to about 50 qubits and a certain number of cycles in a certain amount of time here. And then if you go to more complicated supremacy circuits that can't be mathematically satisfied, that pushes these curves a little bit to the left, and then it gets very hard to simulate them. So Sergio and others have worked very hard on doing the simulations and getting it to work right. And these are the basic ways. There's some more ideas here, but those are the basic ways in which you do it. So let me go on to another. Let's talk about applications now. Although we've been able to show that a quantum computer works really well, and it's big enough so that it's very hard or impossible to do the validations or in the quantum supremacy regime, it turns out this particular algorithm has a useful application. And what's really cool about that is people have talked about how quantum computers can break security and whatever. In this application, quantum computers can actually enhance the security of current systems, okay? And it's through the idea, this is invented by Scott Aronson, of a certified random number generator. And we believe this is going to be the first application of a real application of a quantum computer. Okay, what's going on here? The problem is you have a physical random number generator which has to send its data inside a quantum computer. That physical mechanism certainly can be great, but people always worry whether there's somehow a hacker gets inside the hardware that somehow takes that random number and puts some correlations into it in some special way that you can then exploit in the software. And how do you check that the data that you're getting in software is really coming from a physical mechanism that you know is random and things have not been hacked in between? And this is actually a concern, and people work on verifying their hardware that it's okay, but this is actually something security people are worrying about. The solution is that we can build a quantum random number with a little bit of correlation in it that you can distill away, and that correlation proves it came from a quantum computer, and then you can use the mathematical characteristics of the quantum computer to know it's random. Okay, so how does this work? We come up with a random seed, and then we describe a random circuit. This is what we've done so far and talked about. You then run it on your quantum circuit, and you execute that, and you get bit streams of the random outputs. This is the quantum supremacy experiment. Now, what you do is you timestamp and store this. This is what's new from here. Now, there is some, there's going to be some biases, there's going to be some correlations in that you want to deal with, so it's easy to distill that, all those bit streams down and get an randomness extractor to get a true random number. But this is the new part, is there's a verification part of the algorithm, where in the verification part, what we do is we look at these bit streams, and we look at the circuit here, and we validate that these bit streams had to come from a quantum computer because it has this special speckle correlation that I talked about in the fidelity. The fidelity is big enough that we know it came from a quantum computer. So by doing the cross-entropy benchmarking, we know that the random numbers were created with a quantum algorithm because there's no other way to compute that thing. It's computationally complex. Then you go back and you look at this timestamp and you say, look, we got these bit streams, let's say a second after this seed was made, but we know if we ran a classical computer program, it would have taken a day to get that number. And thus we can validate that the random numbers actually were created in hardware. And knowing it came created with hardware and with a quantum hardware, you can then say we know that these are random, properly random numbers. And that actually is pretty useful for some. It's a little bit niche-y, but it's actually useful. Okay. We're starting to use this quantum computer in running algorithms, and we're not ready to talk much about it here. This is a paper that just came out by Pedram Pedram Rushan in our group, where he was looking at many-body localization in one-dimensional and seeing some kind of entanglement formation grow and decay over time. And then he was able to do that in two-dimensional and show that these kind of shapes and curves look differently. So we're using the Sycamore processor to start looking at different kind of physics. Here, quantum simulation physics. Okay, so this is the second to the last slide, and everyone always is going to ask about the IBM thing. Thank you. Thank you for laughing. That made me feel good. For one thing I would say is we're really thrilled that our experiment was important enough for other people to go out and check it. And not just IBM, but other people are doing, and they're looking at these classical algorithms. So it's really great. The other great thing is with a little bit of controversy here, we've gotten great press coverage. So, we're really happy about that. And, this kind of discussion, of course, in science is good. So we're really happy, and it's nice to address this a little bit. I do want to say, if you want to have a good theoretical discussion of this, Scott Aronson in his blog and a New York Times op-ed actually has a good discussion of this that I really like, and you should read that from kind of a theoretical end. Let me give you my kind of experimental take on this, okay? Now, when we published these results, we knew that people might come out there and find algorithms, classical algorithms, that would simulate faster. And we put in a sentence in our paper because of that, because when you looked at that figure 4A and 4B between the verification and the validation and the supremacy, that's what happened. We thought that the original data was beating quantum supremacy, and then we thought about it and found a trick, and it's like, yeah, okay, someone can be clever and come out. So because of that, we had this sentence in our paper. I don't know if people are reading our paper. Here's the sentence. We expect that lower simulation costs than reported here will eventually be achieved, but we also expect that they will be consistently outpaced by hardware improvements on larger quantum processors. See, when the quantum supremacy, we're kind of trying to hit a moving target. We're trying to exceed a classical computation, and yeah, it's not surprising that clever people will exceed that. We don't think it'll be easy to exceed it, and we think that the quantum computer will essentially do better, but okay, that's okay. Now, so we strongly support validation programs, and listen to me carefully here. I strongly support running validation programs. Why do I say running? Coming up from a proposal for how to run a supercomputer is very different than actually running that proposal on a supercomputer. It's the difference between theory and experiment. And if you're in the computer science community, which IBM is, they know that in that community, if you want to claim something about a program, you're going to have to run it. Now, it's great that you propose it, and that's great discussion, and we'll talk about that and all that's great. But if they want to be serious about claiming something about our experiment, they have to run it. After all, we did an experiment, and we ran it. That's what computer scientists do. So that's great. We're anxiously awaiting. And thank you. And as soon as they show it, that's great. We'll talk about that it happened. And again, we always have this backup plan of this sentence. We worked hard on that sentence, okay. Now, I want to say a couple things about I'm not an expert on this, but it's tricky to write efficient supercomputer code. So you think you know how it scales, but you have to run it. Also, these supercomputers fail all the time. You run a couple-day thing, it may fail, and you may have to restart it and cache it and do other things, which is hard. And in this particular algorithm, where they were storing the quantum state in hard disk, writing the hard disk, this is a non-standard use of disk memory. Again, to really check whether what's going on, you need to run it. So great, we'll do that. And of course, what's great is we've posted all our data, so if they want to check if their program's working right, they can check it against data. I think that's really cool. What I also would say is, in terms of outpaced by hardware improvements, I will absolutely guarantee you that we can build a 57 or more qubit processor in the near future. We tested, this experiment was the first processor we tested, and we did not collapse over the finish line. Okay, we're continuing to make it better. So there might be a nice little race here of whether you can write a supercomputer faster than you can build this, and that's great. We're not particularly focused on doing that because we have to fix many other things and make them better. But they might be a little bit a nice race here that we can talk about. Again, that's good for PR. And then I also want to say, in terms of why we did what we did in our things, we were trying to build these computer simulation programs, not just check for quantum supremacy, but also do validation, and also to be able to simplify our circuit using these lighted circuits, using these cuts, so that we didn't have to spend $1 million to test one circuit. So we can simplify it and validate it and know what's going on. So part of our strategy here was, was to do some kind of computation that was actually reasonable, because we're going to be doing this over and over again to see how it is. So anyway, we're looking forward to seeing what happens with this. And my personal feeling, guess, knowing technology, is that this is really hard. And my guess is no one's ever going to try to run this, in fact. And but we'll see. I would love if people can get this to work. Okay, that's the end of my talk. Thanks for letting me go a little bit more. Implications of quantum supremacy. For computer science, this is great because we challenge the extended Church-Turing thesis. Church-Turing thesis says an abacus is in the same computational class as a supercomputer. One's just faster and bigger than the other. And of course, what we're talking about in a quantum computer is a new class of computational devices. And clearly, we want to make it bigger and more powerful and error-corrected, but we're beginning to see that challenge. In terms of physics, this is great. We know physics works for extremely complex quantum systems, which has never been probed before. And of course, you need that to happen to be able to use that physics to build a quantum computer and doing things with it. In terms of engineering, we built a new architecture with these adjustable couplers and gotten that to work. And the systems test of that system works really well. We know how to control it. We know what all the errors are doing. And the system works good. In terms of useful or maybe business here, we have the first application. It's being developed. We're excited about doing that. And now we're looking for the second application. And we're hoping maybe people out in the audience here can start thinking about it, maybe get on our quantum computer when we get in the cloud, and help us develop these applications, in which case the field will really start to take off, be able to do amazing things in the future. So everything looks great. Really looking forward to the future. Next 5-10 years will be really, really interesting for us. Thank you very much.